Hello and welcome to Controllers Tech. In today's video, we'll learn how to interface the SHT21 temperature and humidity sensor with an STM32 microcontroller. Over time, we have worked with several temperature and humidity sensors, but the SHT21 stands out as one of the simplest and most reliable sensors to connect and interface with STM32 boards. The SHT21, developed by Sensirion, is a digital temperature and humidity sensor known for its compact size and dependable performance. It communicates using the I2C protocol, which makes it extremely easy to connect with microcontrollers such as the STM32. One of the biggest advantages of the SHT21 is that it provides fully calibrated and linearized digital outputs. This means we can directly read accurate temperature and humidity values from the sensor without needing additional calculations or external components for signal conditioning. In this tutorial, I'll be using the STM32F103C8 microcontroller to interface with the SHT21 sensor. Here is the datasheet of the sensor. We'll go through the key sections of the datasheet later in this video to better understand how the sensor works and how to use it effectively. I have already prepared the library files required to communicate with the SHT21. Don't worry, I'll explain the important parts of the library with reference to the datasheet in a few moments. You can download these files from the project link provided in the description below this video. Now, let's open STM32 CubeIDE and create a new project. As mentioned earlier, I'll be using the STM32F103C8 board for this demonstration. Give an appropriate name to your project, and once that's done, click Finish. We'll begin by setting up the clock configuration. Here, I'm selecting the external crystal oscillator to provide the clock source. The blue pill board comes with an 8 MHz crystal on board, and we'll use the PLL to boost the system clock to its maximum speed of 72 MHz for better performance. Next, navigate to System Debug, and enable Serial Wire Debug. This will help with debugging during development. Now let's move on to configuring the I2C interface, which we'll use to communicate with the SHT21 sensor. In this setup, I'm using I2C1, where PB6 and PB7 are configured as the SCL, clock line, and SDA, data line, respectively. I'll keep the I2C configuration in standard mode with a clock speed of 100 kHz. However, you can also switch to fast mode, 400 kHz, if you prefer higher data transfer speeds. The SHT21 sensor supports it without any issues. Next, let's enable UART1 to view the sensor readings and debug logs on a serial console. Here, the TX pin of the STM32 is connected to the RX pin of the USB to UART module. That completes the basic configuration in CubeIDE. Once everything is set up, click Save to generate the project code. Let's take a look at the connection diagram for this project. Here, you can see how the SHT21 sensor is connected to the STM32F103, along with the FT232 USB to UART converter module. The SHT21 sensor communicates with the microcontroller using only two pins, one for data and one for clock. The remaining two pins are used for power supply. The sensor operates at 3.3 volts. Which is conveniently supplied directly from the STM32 board. In this setup, the SDA pin of the SHT21 is connected to PB7, I2C1 SDA pin, and the SCL pin is connected to PB6, I2C1 SCL pin. Additionally, the UART1 TX pin of the STM32 is connected to the RX pin of the FT232 module. This connection allows us to log and monitor data from the sensor on the serial console of the computer. That's all for the hardware connections, simple and clean. Now let's move forward with the project setup. The first step is to copy the library files into your project directory. You can download these files from the project link provided in the video description. Let's begin by taking a look at the SHT21 header file. In most cases, you don't need to modify anything here. However, if you face any communication issues while interfacing the sensor, you can enable the debug logs to get detailed information on what's happening behind the scenes. For this tutorial, I have only enabled the user logs, which will display the temperature and humidity values on the console. Another important part of the header file is the device address of the SHT21. It is defined as 0x80. Now, if you refer to the sensor's datasheet, you'll notice that the 7-bit I2C address for the SHT21 is 0x40. The reason it's defined as 0x80 in our code is because the STM32 HAL library expects the 8-bit write address. To get that, we shift the 7-bit address, 0x40, to the left by 1 position, effectively making it 8 bits wide, which results in 0x80. This is the address that will be used to communicate with the SHT21 over I2C. Also note that the sensor supports I2C clock speeds up to 400 kHz, so you can use either normal mode, 100 kHz, or fast mode, 400 kHz, both work perfectly fine. Next, in the header file, I have defined a few commands for the SHT21. These commands come directly from the device datasheet, and I've simply listed them here for convenience. Since the SHT21 operates with only a small set of commands, it is one of the easiest sensors to interface with the STM32. Now, let's open the SHT21 source file. Here, the only change you need to make is to declare the I2C and UART instances that you're using, for the sensor communication and for serial logging. Once that's done, you don't need to modify anything else. The library handles all the low-level operations internally, making the integration process straightforward and efficient. Let's now take a quick look at how this library actually works and understand what happens behind the scenes. The first function in the library is SHT21init, which is responsible for initializing the sensor. This function simply calls another function called soft reset, which resets the sensor back to its default configuration. According to the sensor's datasheet, after performing a soft reset, the SHT21 automatically reinitializes and starts operating with its default settings. In this default configuration, the humidity resolution is set to 12 bits, while the temperature resolution is set to 14 bits. If you want to modify these settings, you can do so by writing to the user register of the device. The library already provides functions to read and write the user register, so you can easily update the configuration by passing the desired 8-bit value as a parameter to the write function. Throughout the library, the communication between the STM32 and the SHT21 sensor is handled using the standard HAL I2C functions. HAL I2C master transmit is used to send commands or data to the sensor, and HAL I2C master receive is used to read data back from the sensor. Next, we have the SHT21 read raw function, which is responsible for reading the raw temperature and humidity data from the sensor. The command parameter passed to this function determines whether it will read temperature or humidity values. If you refer to the datasheet, you'll notice that there are two separate commands to read the temperature, one is for hold master mode and the other for no hold master mode. Let's briefly understand the difference between these two modes. In hold master mode, the clock line is blocked by the sensor during the measurement process. Essentially, the sensor pulls the SCL line low, forcing the master, in our case, the STM32, into a wait state. Once the measurement is complete, the sensor releases the clock line, signaling that the data is ready to be read. While the clock line is held low, the master cannot communicate with any other I2C devices on the bus. In contrast, The no-hold master mode allows the clock line to remain open during measurement, meaning the master can still communicate with other devices on the I2C bus while the SHT21 is busy. However, in this mode, the master must periodically check or poll the sensor to determine when the measurement is complete. As shown in Table 7 of the datasheet, the maximum measurement time for the SHT21 is approximately 85 milliseconds. To ensure accurate readings, the MCU can simply wait for about 100 milliseconds before attempting to read the data. Inside the read raw function, once the trigger command has been sent to start the measurement, the MCU waits for this 100 milliseconds delay, and then it reads 3 bytes from the sensor. The first 2 bytes contain the actual sensor data, either 14-bit temperature or 12-bit humidity, depending on the command used. The third byte contains the CRC, which is used to verify data integrity. After receiving the data, the program compares the CRC sent by the sensor with the CRC calculated from the received data. If the CRC check passes, the 2 data bytes are combined to form the final 12-bit or 14-bit raw value. Before converting this raw data into physical values, we clear the 2 least significant bits. This step is specifically recommended in the datasheet, as these 2 bits must be set to 0 before performing the final calculations. Now, let's see how to convert this raw data into meaningful temperature and humidity values. Inside the SHT21 read temperature function, the raw temperature data is first read using the no-hold master mode. Once the raw value is obtained, it's converted to degrees Celsius using the formula provided in the datasheet. This ensures that the temperature readings are both accurate and properly scaled. In a similar way, we read the humidity data and convert it into relative humidity, in percentage, using the corresponding formula also mentioned in the datasheet. Now let's see how to use this library in our main code. Start by including the SHT21 header file in your main.c file. Next, define a couple of float variables that will be used to store the temperature and humidity values received from the sensor. Inside the main function, once you have initialized the I2C peripheral, call the SHT21 init function to initialize the sensor and prepare it for communication. Within the infinite loop, continuously read the temperature and humidity values using the library functions and store them in the variables we defined earlier. After each read, log the temperature and humidity values to the serial console so that we can observe them in real time. When printing the humidity value with a percentage symbol, remember that in C language, you need to insert the % character twice in the printf statement to display it correctly. Let's add a delay of 500 milliseconds between successive readings to avoid unnecessary rapid polling of the sensor. Once that's done, build the project and flash it to the board. After flashing, open the serial console to view the output logs. At first, you might notice that the log messages appear, but the actual temperature and humidity data are missing. This happens because by default, floating point support in printf is disabled in STM32 CubeIDE. To fix this, go to Project Settings, C++ Build, Settings, MCU/MPU Settings, and enable the option for using float with printf. Now, build and flash the project again. This time, you'll see the temperature and humidity readings printed correctly on the serial console. However, you might notice that the readings don't change immediately, even when you hold the sensor with your hand. That's because our delay between measurements is too short. The SHT21 needs a bit of time between reads for stable results. To fix this, increase the delay to at least 1 second between successive readings. Now, when you run the program again, you'll see that new readings are displayed every second, and the values change dynamically. As I hold the sensor, you can clearly observe that both the temperature and humidity values start increasing. The temperature quickly rises to around 32 degrees Celsius, and once I release the sensor, both the temperature and humidity levels gradually decrease, returning to normal. This confirms that everything is working perfectly. We've successfully interfaced the SHT21 temperature and humidity sensor with the STM32 using the I2C communication protocol. The SHT21 turned out to be extremely simple to interface. With just a few commands, we were able to obtain accurate and reliable temperature and humidity readings. One important thing to remember is to avoid reading the sensor too frequently. Always include at least a 1-second delay between consecutive measurements to ensure stable and accurate results. That's it for today's video. I hope you now have a clear understanding of how to interface the SHT21 sensor with an STM32 microcontroller. You can download the complete project from the article linked in the description below this video. If you have any questions or face any issues, feel free to leave a comment, and I'll be happy to help. Thank you for watching, and as always, keep learning, keep experimenting, and have a great day ahead.